Hello everyone. We will begin in another 2 more minutes. Hello everyone. We will begin in another 2 more minutes. Hello everyone. We will begin in another 2 more minutes. Alright, let's begin right now. Hello everyone, I'm Mr. Tan and you are watching chemistry tutorial. Let's get into it. For today's live session, I'll be going through the Raffles Institution RI 2018 Year 6 Prelim Chemistry paper. It will be a paper 1 MCQ paper. So without further ado, let's have a look at it right now. Okay, a sample of iron contains 3 isotopes, iron 54, iron 56, and iron 58. Its relative atomic mass is 55.849. One of the isotopes has a percentage abundance of 91.8%. Now, if you look at the values given, you notice that 55.846 is actually closer to 56, iron 56. So you should expect that iron 56 probably has a percentage abundance of 91.8%. Hence, Y itself should be 91.8 using pure logic. So that means we are only left with 2 options, either B or C. This is where you can start to compute the values using your calculators. So for question 1, you can just do, because once you have 4 options and you can eliminate just 2 options, you're left with 2. So you just work on the other 2. So I just work on the correct answer in this case, which is 6.37 over 100 multiplied by X is our 53.94 plus 91.8 over 100 times 55.94 plus 1.83 over 100 multiplied by 57.93. You do your calculations, and it turns out that indeed we do have a percentage abundance, or rather the relative atomic mass as 55.849. Okay, now let's move to question 2. As to CRX disproportionates, completely in water to give S and SO2 in a ratio of 3:1. So how do we do this question? For question 2, we have S2ClX reacts, this proportion is completely in water. That means we need to add water plus water to produce sulfur plus sulfur dioxide in a ratio of 3:1. Now notice that you have 3 sulfur, therefore you should put a 2 over here. Now next, so you have 4s. Now how about this O? You notice you have 2 oxygen here. So actually there's another product in form, which is your HCl, because you have H and the Cl, so you probably should expect the formation of HCl as well. So we have 4s, now we have 2O, so we are going to put a 2 over here, so you have 2 O's. But then we have 4H, that means you're going to put a 4H over here at the HCl side, meaning you have 4Cl. So our X shall be just 2, because 2 times 2 gives us 4. Hence, answer for question 2 is A. For question 3, which ion would undergo the greatest deflection in the electric field? Now, the angle of deflection is actually dependent on the angle of deflection is proportional to charge over the mass. So if you look at option A, the charge is +1. The mass is 30 because 15 times 2. So let's compute the values. So 1 divided by 30, so we get around 0.0333. That's for option A. For option B, we have +2 over the mass of CO, which is 12 plus 16, which is equals to 28. So 2 divided by 28 gives us 0.0714. That's for option B. Now for option C, we have +3 over CO2, which is 12 plus 16 times 2, gives us 44. So 3 divided by 44, what we have is 0.0682. That's for option C. For option D, we have +2 over the mass of oxygen, which is 16 plus 18, gives us 34. So 2 divided by 34 will get 0.0588. That's for option D. So if you want choose the ion that undergoes the greatest deflection, then we need to check which value is the largest. So in this case here, what we have is the one which is the largest. Let me check. Hold on a minute. B itself, right, is 3 plus over. Oh, I made a mistake over here. Yeah, because otherwise I should be choosing B, right? Am I right? But the answer is C. I realized I made a mistake because for B we have 3. This is for B, right? Okay. Let me see. This is B. I put it wrongly. Sorry about that. This is C. Yeah, because 1 over 30, that's for A. Then B is the carbon dioxide, so it's 44. Yeah. Then C is over here. Yes, correct. So therefore, you have to choose the one with 0.0714. Therefore, the answer for this is C. Okay. Now, the next one we look at is question 4. Now, question 4 has to do with radioactive decay. Okay, it's not that difficult actually, because you have 241 95 AM gives you 42He plus E. Now then, what is the mass number? Just 241 minus 4, which gives us 237. How about the proton number? 95 minus 2. So it gives us 93. So how many protons do we have? We have 93. So we should only consider C and D. What's the number of neutrons? It's not 237. 237 is the number of nucleons, which comprises protons and neutrons. So to get 144, we will use 237 minus 93. And this one will give us 144. Hence the answer is option C. For question 5, which statement about both molecules shown below is correct? So let's look at option A. Both can turn hot acidified potassium dichromate from orange to green. Now let me draw the structures of these two molecules first. So you have a phenol group and you have a phenolic ester. This is your methyl group. Versus the other one, we have a phenol. At the same time, we have our benzaldehyde and aldehyde group. Now, both can turn acidified potassium dichromate from orange to green. That's not possible because if you want to oxidize this, you must use KMnO4. Potassium dichromate won't work. So A is already out. For B, both can form intramolecular hydrogen bonding, G can form intramolecular hydrogen bonding while F cannot. That's not true because, let me reorientate these molecules. You have a O, you have a H. You have a C, you have a O, you have a C, you have a O, you have a CH3. So over here, the oxygen has a lone pair. It carries a delta minus charge, delta plus. So it can actually form a intra-hydrogen bond over here for the molecule F. So you can't say that F cannot form intramolecular hydrogen bond. How about G? G itself can also form intramolecular hydrogen bond. Why? Because you have OH. So let's orientate the molecules a little bit. Right, so there's a lone pair, delta minus, delta plus. This H is bonded to a highly electronegative element, which is oxygen. And then now it can actually form a hydrogen bond. So for option B, it is wrong because both F and G can form intramolecular hydrogen bonding. Now, let's look at D first. Both molecules are planar. That's not true because, yes, the benzene ring itself is planar because it's sp2 hybridized. The carbon atoms are all sp2 hybridized. But if you check over here, you have a methyl group. This is sp3 hybridized, which means that you adopt tetrahedral shape, which is not planar. Similarly for here, actually this oxygen, it will be band shape or V shape with respect to the oxygen atom, so it's not planar. There's a band shape with respect to O, triangular planar with respect to C. So definitely option D is wrong. Now, in that case, this leaves us with the only correct option, which is option C. So both molecules have the same number of pi electrons. So let's check how many pi electrons do they have. We know that the benzene ring itself has 6 pi electrons. And over here also 6 pi electrons. Right, so most of us will probably think that F and G have 6 pi electrons. However, I will beg to differ because I believe that actually there's another pi electrons available for the OH. Because your oxygen over here is actually sp2 hybridized. It has a lone pair that's in the unhybridized p orbital, and that's the reason why it can delocalize into the aromatic ring. So what we have is actually 6 plus 2 gives us 8 pi electrons. Now the phenol itself is actually aromatic, right? Some people may think that, oh, 8 pi electrons means it does not fulfill the Huckel's rule. Huckel's rule of 4n plus 2, right? But actually, you need to know that to fulfill Hakel's rule, not only you need to have 4n plus 2, at the same time, the molecule must be planar, cyclic. So we are not going to include the pi electrons from the OH. Therefore, this is still aromatic. But I've already sidetracked quite a bit. So both molecules should have 8 pi electrons. Now, let's look at question 6. Question 6 itself, we need to use PV equals to nRT, the ideal gas equation. So PV equals to nRT. Now, if I tell you that we have a fixed mass, that means your N is fixed. Number of moles is fixed. Molar gas is a constant, so this is also fixed. Technically, what we have is PV equals to KT, where K is your NR. So let's look at option A first. So now, you are supposed to have the y-axis as P over T, so just bring this T over. What we have is P over T is equals to NR over V, where NR is a constant, which means that P over T is proportional to 1 over V. Hence, the graph, what we have is a hyperbola. It's very similar to saying that if, let's say, y is proportional to 1 over x, then what we have is just y over x with a hyperbola shape. Right, this requires a bit of mathematical knowledge. Let's look at option B. Option B is the one at the bottom. I don't want to mistake as the one on the right side. Okay, so for option B, okay, what we have is, okay, PV equals to nRT. Since the mass is fixed, so N is fixed, R is a constant, so R is fixed. Now, we also have a constant P, so P is fixed. So that means V over T is equals to NR over P. This whole thing is a constant. That means if we were to sketch the graph of V over T against anything, it doesn't matter what the x-axis is, it will be just a horizontal line because V over T is a constant. However, in this case, our V over T is on the x-axis. Therefore, for option B, V over T, regardless of what this is, we should have this line because you just tilt this graph clockwise or anti-clockwise or 90 degrees clockwise. You're going to get this shape. So B is wrong. Let's look at option C. Okay, PV equals nRT. NR is fixed. Now, density. Now, the thing is, density is mass over volume. So, PV equals to number of moles is mass over MR or AR multiplied by RT. Bring the volume over. So, P is equals to mass over volume multiplied by RT over MR. Now, since the mass is fixed and we are using that same gas, so actually MR is fixed. They told us, so MR is fixed and T is also fixed based on the question. So technically speaking, this whole thing is a constant. That means P equals to M over V, and M over V we know is density. So P is equals to density times RT over MR, where RT over MR is a constant. Hence, this is similar to having sketching a graph of y equals to kx. In other words, the graph for option C should look something like this. What we should have is actually a straight line passing through the origin and not a curve that flattens out at the end. It should be a straight line passing through the origin. So option C is out. Option D, let's look at option D. Okay, PV against T. So PV equals to nRT. NR is fixed. So now, technically speaking, what we have, you are trying to plot PV against T. So actually the graph should look like this. Because T is in Kelvin, based on the question, assume that all temperatures are measured in Kelvin. So in that case, we should also have a straight line passing through the origin 0. In order to get the graph that is suggested by option D, we can get that. However, this T must be expressed in degrees Celsius. So that over here, what we have is actually minus 273 degrees Celsius. Because that's your 0 Kelvin. Minus 273 degrees Celsius is your 0 Kelvin. Okay, so therefore the answer for question 6 is option A. Let's look at the next question, which is question 7. Use of data booklet is relevant to this question. Methane undergoes free radical sub with bromine in the presence of UV light. Which energy profile diagram represents the propagation steps that lead to the formation of bromomethane? We know that for FRS, free radical sub, there are 3 steps. Initiation, which is to generate the radicals, propagation, and lastly, the termination. So now, from the initiation, you already have a radical. So now for propagation, what we have is we are having our methane, CH4, and we already have a radical that was generated based on the initiation step. So now I need to draw the mechanism, the arrow pushing, so that you can actually appreciate how to solve this question. So notice that this is a fish hook. What we have is we're going to get a methyl radical plus HBr. That means you are actually trying to, so we need to calculate the enthalpy change for this case. So an enthalpy change for this case is that you are actually breaking the CH bond. This is where we need to refer to our data booklet. Right, let's check the bond energy of the CH bond. So the bond energy of the CH bond is 410. So over here is 410. But you are trying to form the HBr bond. So the bond energy of HBr is 366. You need energy to break the bonds. So over here, this will be a positive value, plus 410. So you are forming HBr, that means 366 kilojoules of energy is released. So exothermic, negative sign. So plus 410 plus minus 366, what you have is simply plus 44. That means it is an endothermic step. Next, once you have this radical, methyl radical, you'll react with your BR to form your RX, your bromomethane, with the generation of the bromine radical. So let me write out the mechanism. Fish hook, half arrow. So that means here you are trying to break the BR bond. So let us refer to the data booklet and check what is the bond energy for BR. 193. But here you are forming the CBr bond, which is 280. So now, because you are breaking the bond, so you require energy, so this will be a positive 193. Forming the bond, so it's negative. So the enthalpy change for this step is actually plus 193 plus minus 280, which will be a negative value. 193 minus 280, which is minus 87. Now, that means the first step is actually endothermic. The second step is actually exothermic. Bear this in mind. So with that, that means the only reasonable answer is actually option B. Why? Let's try to understand this a little bit. Notice that over here, what we have is a positive delta H, right? Because in the previous step, what we saw was that the first step, what was the delta H? Let me refer. Delta H was plus 44 versus minus 87. So plus 44, the second one, delta H is minus 87. So over here, what you have is you have plus 44. That means this is your reactant, this is your product. But after that, this is your product, and now this is your reactant, now this is your product. And now this part itself is actually equivalent to minus 87. So you find the difference between 87 and 44, you are able to get the overall enthalpy, which is simply just positive 44 plus negative 87, which gives us the enthalpy of this particular step, which is minus 43 kilojoules. Hence, the answer for this question is just option B. Now let's look at question 8, which is not a trend from left to right across the elements of the third period of the periodic table. Option A is definitely correct. So let me see. Let's consider option A first. Option A is a trend. Why? Because as you go across the period, the oxidation number will increase from +1, +2, +3, +4, +5, +6, +7. That means from +1 of group 1 element to +7 of your group 7 or group 17 element. So definitely the maximum oxidation number does increase. So A is correct in the sense that it is a trend. Now B itself, the melting point of the oxide decreases. That's not true because, now let me just sketch this graph. Now you need to realize that the melting point of Na2O is lower than that of MgO, but MgO's melting point is actually higher than Al2O3. After that, from here onwards, you have your SiO2, etc. So as you can see that it's not absolutely decreasing because over here there's an increase before suffering a drop. So option B is not a trend. Now for option C, the pH of aqueous solution of the chlorides decreases. That's a trend because NaCl has a pH of 7. MgCl2 has a pH of 6.5 because it has 2+ high charge density, so it's able to undergo hydrolysis in water to give you H+ ions. AlCl3, very high charge density, so it gives you pH of around 3. The next one that we have is SiCl4, which will undergo hydrolysis in water. For example, SiCl4 plus water gives you SiO2 plus HCl. Now some notes you'll write as SiOH4, for instance. It doesn't really matter, but this will give us around pH equals to 2. Next one that we have is PCl3 or PCl5, which will give you H3PO4 or H3PO3 with the evolution of HCl. And HCl, we know that it's a very strong acid, so it gives you around pH 1 to 2. Definitely the pH of the aqueous solution will decrease. So option C is definitely a trend. Okay, so let me just shift this a little bit further so you can see. Now how about for option D? The nature of bonding of the chloride changes from ionic to covalent. That's true because NaCl is an ionic compound. MgCl2 is an ionic compound. AlCl3 is simple covalent structure, simple molecules. SiCl4 also simple molecules. PCl3, PCl5, etc. These are also simple molecules. So definitely the nature of bonding changes from ionic to covalent. Hence, the answer for question 8 is B. Let's look at question 9. Elements J, K, and L are elements in period 3 of the periodic table. The melting point of element J is higher than that of element K. Only the oxides of element L is insoluble in water. So, if you know your periodic table, let us just write the oxides out first. Okay. Now, so we have Na2O, we have MgO, we have Al2O3, we have SiO2, we have things like P4O6, P4O10, we have SO2, and then SO3, etc. Now, this is soluble in water because it gives you around pH 13 to 14. This one is also soluble, gives you pH around 9 to 10. This is insoluble in water, gives you pH 7. SiO2 as well, pH 7. They are not soluble in water. P4O6 and P4O10 will give you acids such as a phosphoric acid, H3PO4, H3PO3. So it gives you around maybe pH 2 to 3, etc. 1 to 2 or 2 to 3. Okay, so you notice that only your Al2O3 and SiO2, they cannot dissolve in water. Therefore, L itself must be either aluminium or silicon. So you just need to look at your options given. So A is definitely not correct because you notice that L is magnesium. Alright, so you should only consider option B, C, and D because SiO2 is insoluble in water, Al2O3 is insoluble in water, and SiO2 is insoluble in water. Now the next one is this. They said that the melting point of J is higher than that of K. So just look at this itself. I mean B, C, and D. Sodium, does it have a lower melting point than magnesium? Or does it have a higher melting point than magnesium? Wrong. It has a lower melting point because sodium and magnesium are metals. So metallic bonds, strength of metallic bonds depends on the valency. So sodium has a valency of 1, magnesium has a valency of 2. So magnesium must have a higher melting point than sodium. So option B is out. The same applies for option C because sulfur, despite having a greater AR, which is 32 versus 31 of phosphorus, but I need to know that sulfur typically exists as S8. Phosphorus typically exists as P4. So in terms of the MR, or the number of electrons per molecule, S8 definitely has more compared to P4, which means that the strength of its IDID is stronger for S8 than P4. That's because they adopt simple molecular structure. That means you must look at their intermolecular forces, in this case IDID, instantaneous dipole, induced dipole. Therefore, option C is out. That means the only answer is option D. Now, let's look at the question 10. Question 10, a reaction kinetics question. So the reaction between NO2 and SO2 is a key stage in the formation of acid rain. A series of experiments was conducted with various concentrations of NO2 and SO2 in the absence of air. So now we are given a half-life so and so. Which row gives the correct half-life of NO2 in experiment 2 and 3? Now to solve this question, first we need to be able to determine the rate equation. In other words, we need to know the order of reaction of NO2 as well as SO2. Let's call this X and Y first. Now, to determine the order of reaction with respect to NO2, we can actually compare experiment 1 and 2. 1 and 2. Because the concentration in this case of SO2 is fixed. So notice when the concentration of NO2 doubles, the relative rate also doubles, which tells us that the order of reaction with respect to our NO2 is simply first order. Alright, of course, there's no need to put a 1, but I'm just putting 1 for your reference. Now, then we need to find out the order of reaction with respect to SO2. So let's check. Okay. Now, in this case, you notice that since we already determined, or we have already determined that the order of reaction with respect to NO2 is 1. So when this doubles, okay, you should expect the rate to double to give you 4. That means this should be 4. But you notice when the concentration of SO2 also doubles, this becomes 8. In other words, the order of reaction with respect to SO2 is also 1, which means that the overall order is actually 2. Now, if it's first order, that means typically we can actually use this equation, this formula, this expression. Half-life is actually ln 2 over K, where K is your rate constant. However, you need to appreciate that in our school notes, what we are working with is usually just a single reactant. That means A gives you P. Alright, and if it's the first order kinetics, then what we use is just rate is equals to Ka. Now bear in mind that there's only a single reactant for all the examples that we see in our notes. Hence from here, what we have is half-life is ln 2 over K. Now, take note now, if you are trying to find the half-life of A, the A cannot appear here. Okay, if you understand this critical factor, now we can actually solve this question already. Because now, rate is equals to K NO2 SO2. Okay, now because the question told us that the half-life of NO2 in experiment 1 was 48 seconds, in other words, this half-life is meant for NO2. So in other words, what we have is actually ln 2 over K prime. And ln 2 over K prime. So now, let me just rephrase this again. You can actually re-represent this as what? Rate is equals to K prime NO2. K prime NO2, where your K prime is actually K times the concentration of SO2. So now, we replace this K prime with ln 2 over K times the concentration of SO2. Now, in most school notes, right, they always say that for first order kinetics, the half-life is independent of concentration. That's only partially correct. Because if you only have one reactant, yes, then it's independent of concentration. But what happens if you have more than one reactant, such as 2 reactants in this particular scenario? Then you notice that the half-life is actually dependent on the concentration. So if you compare experiment 1 and 2, okay, you notice for experiment 1 and 2, the concentration of SO2 is the same, 0.2 and 0.2. So therefore, the half-life for experiment 2 should also be 48 seconds. 48 seconds, because the 48 here, you have 48 seconds. That means we should only consider option C and D. But for experiment 3, you'll notice that right now, experiment 3, the concentration of SO2 has actually doubled from 0.2 to 0.4. So in other words, that means when your concentration of this has actually doubled, that means your denominator has doubled, which means your half-life must reduce by half, by 2 times. Therefore, the half-life in experiment 3 is 24 seconds. Hence, answer is option C. Okay? Now, let's move to question 11. Question 11 is a trick question. It's a bit tricky. Now, the thing is, to solve this question, obviously we must find the order of reaction with respect to M and hydroxide. So let me just write a general expression first, which is rate equals to K M, I just put an X here, and OH minus, I just put a Y here. Now, for this example, a lot of students will probably think that, okay, when the concentration of M, or rather, you notice that the total volume is kept constant. Check this out. For experiment 1, 2, and 3, the total volume is 15. Because 1 plus 10 plus 4 gives you 15. For experiment 2, 2 plus 10 plus 3 gives you 15. For experiment 3, 1 plus 5 plus 9 gives you 15. We need to keep the total volume constant by adding the required amount of water. So that when the total volume is constant, that means any change in the volume of this reactant will be proportional to the change in concentration of that particular reactant. So notice that when the volume doubles, effectively we are seeing the concentration doubles since the total volume is kept constant. But then there's no change in time. And because of this, a lot of people have concluded that the order of reaction with respect to M is 0. That's wrong. That's because you always need to consider whether the reactant itself is a colored species. I've explained this in more details in my book, A-Level Chemistry Best Kept Secrets, over this sort of questions. Now, in short, what I want to tell is that if the reactant is colored, okay, so if we have a colored reactant, we must always use the volume of the colored reactant over the total time. Volume of the colored reactant over total time. That means you must re-express the rate as V over T, not 1 over T. So in other words, I'm going to draw a new self table. Okay, so over here we have the volume of your M, we have the hydroxide, we have the water, we have the time. Okay, but now this will be my rate, but my rate will be V over T. So now 1, for experiment 1, this is 1, M is 1. For experiment 2, this is 2. Hydroxide is 10, 10. Water is just 4 and 3. Time is 100, 100. But now, the rate itself, you have to change it to 1 divided by 100. Why 1 divided by 100? Because 1, that's a colored species, divided by the total time. So 1 over 100 is 0.01. That's your relative rate. Okay, we don't have to care about units. That's a relative rate. Over here, it will be 2 over 100. 2 over 100. In other words, this will be 0.02. That means when the volume doubles, concentration doubles, the rate also doubles. Hence, it is first order with respect to M. Therefore, your statement 1 is correct. This statement 1 is correct. Okay, always remember this. If your reactant is a colored species, your rate cannot be 1 over T. You must use the volume of the colored species over T. So option 1 is correct. Now let's look at option 2. Option 2. Is the order of reaction first order with respect to OH minus? Well, you notice that we can actually just compare experiment 1 and 3. 1 and 3. Okay? So you notice that when your volume doubles from 5 to 10, the rate actually halves. Okay, the rate actually halves. I would suggest that for this case here, what you do is you still use this rate, which is in this case 1 over 200 versus 1 over 100. Then you notice that when the volume doubles, the rate actually halves, which means that it's first order with respect to hydroxide. Now for statement 3, probably some people have chosen statement 3 as well. That means you choose option D, because they think that, okay, if I look at experiment 2 and 4, the volume doubles. So that means, since it's first order, as determined in statement 2, that means the time taken should actually half. You should expect 50 seconds. But that's not correct, because you notice that the total volume for experiment 4 itself is actually not 15 for experiment 1 to 3. In fact, this is 30. So if the question ever asks us to find the total time taken for the pink color to fade, how shall we do this question? Well, there is a way. In fact, the answer, the time taken should be 200 seconds. Let me show you how this is done. Let us just take the data from experiment 1. So what we have is rates is equals to K, M, and OH minus. We need to find the rate constant. So what's the rate here? Well, I'll just use 1 over 100. I'm using the data from the first experiment, 1 over 100. Okay? Equals to K. But what's the concentration of M in this case? I'm going to use 10 over 15. Why 10? Because you have 10 cm, the volume is 10 cm cubed over the entire volume, which is 15. Oops, I think I made a mistake. Should be 1. Yeah, should be 1 over 15. My fault. Sorry. Yeah. It should be 1 over 15 because M over the whole volume is 15. Then for hydroxide itself, it will be 10 over 15. Okay, so you need to find out what the K is. Right, just press your calculator, find out what your K is. And turns out that your K is actually 0.225. There's no need to be concerned too much with the units. Okay, so this will be 0.225. So now we're going to take the data for experiment 4. So which is, now we need to find what the T is, right? I put a capital T here. All right, I'm going to choose 2 over T. 2 over T because the volume of the color species is 2 over T. Right, that's a rate. Equals to, now I can put in the K as 0.225. Why can I use the same K value? Because K is your rate constant. Rate constant is dependent on temperature and the use of catalyst. So therefore, since we are not changing any of the conditions, the K will be the same. And what's the M? The M in this case will be 2 over the entire volume, which is 30. So 2 over 30 times 20 over 30. So here, you try to find out what your T is. So 0.225 times 2 divided by 30. It turns out your T is actually 200 seconds. Hence, statement 3 is wrong. Therefore, the correct answer is just 1 and 2. Okay, so I must admit that this question is a bit tricky. The same applies for question 10. Now let's look at the next question. Question 12. Consider the following reversible reaction. So Q gas, Q plus R gives you S. So this is a gaseous system. So Q gas plus gaseous R to give you gaseous S. And this is an exothermic reaction. So after equilibrium was reached, the system was disturbed and the changes to the system were monitored. The changes were as follows. So, okay. So what was the disturbance applied? Now notice that there's no change in K. K is your equilibrium constant. So equilibrium constant can only be changed if there's a change in temperature. In other words, actually option B is out. Okay, so let me just write out the possible options A, B, C, and D. Right, because the Kp remains unchanged, so that means there's no change in temperature. So option B is out. Now, is there any use of catalyst? Now, yes. The thing is, if we use a catalyst, yes, we do have both the forward rate and the backward rate increasing. That's correct. However, the use of catalyst will not affect the yield. It just speeds up the forward rate and the backward rate. But here, the concentration of S, the concentration of product actually increases, which means that we cannot choose option A. Always take note that the use of catalyst only increase the forward rate and the backward rate. It does not affect the yield. So A and B are out. Let's look at option C. There's a compression of the reaction mixture. So if you compress the reaction mixture, that means you are trying to reduce the volume. When you reduce the volume, that means you are trying to increase the pressure. So based on the Chatter's principle, the system will respond in such a way as to increase overall pressure by favoring the sites, or rather, you try to increase the pressure of the system. You try to respond in such a way to decrease the overall pressure. Based on the Chatter's principle, it wants to decrease the pressure. How does it decrease the pressure? By favoring the site with lesser moles of gas. And notice that based on your reversible reaction equation, this side has 1 mole of gas, this side has 2 moles of gas. Hence, more product will be formed. Hence, the correct answer is C. However, let's look at option D. The addition of inert gas at constant volume actually does not affect the position of equilibrium. In other words, yes, it will not cause any change in the concentration of S. Hence, the only correct answer is just option C. Now, for question 13, the graph below shows how the fraction of NH3 gas in the equivalent mixture of the Haber process varies with temperature of pressures of P1 and P2. So in which row is the table correct? Now to do this question, okay, so for question 13, Haber process N2 plus 3H2 to give you 2NH3, okay? Delta H, the forward reaction is we do not know, but actually if you know Haber process, you should know that this is actually an exothermic reaction. But let's assume we do not know. So let's try to interpret from this diagram. So the concentration of NH3 versus the temperature. So just what we have is actually a hyperbola shape. So that means from this shape itself, what it tells us is that when there's an increase in temperature, that means there's an increase in temperature, the concentration of NH3 actually drops. In other words, there's a drop in the concentration of NH3. And NH3 happens to be on the product side, which means there's a drop in the concentration of the product. So, what does it tell us about the enthalpy? think of it this way. If this itself is exothermic, technically speaking, it seems to suggest that the temperature over here is actually slightly hotter. Okay, I'm using a layman way of explaining. That means heat is released, so this side is actually hotter, which means that the reactant side is actually a bit colder. So when you increase the temperature, based on increase the temperature based on Le Chatter's principle, the equilibrium will shift towards the side that is a bit colder. That means it's going to shift towards this side. Why is it hotter? Because this is exothermic. In other words, your product concentration will drop. Because of this, that means we should only consider option A and B, whereby X itself, the enthalpy change is exothermic. Now, how about the pressure side? I'm going to add one more, which is this one. Now, for the same temperature, do you notice this side, this one is pressure P2. Over here, this is pressure P1. At the same temperature, okay, at same temperature, okay, you notice that the concentration of NH3 at P1 is actually larger than the concentration of NH3 at P2. So what does it mean? It tells us that P1 must be greater than P2. P1 must be greater than P2. Now, how do we explain this? You see it this way. If the pressure is higher, now you notice that you have 4 moles of gas over here and 2 moles over here. So if the pressure is higher, based on Le Chatter's principle, the position of equilibrium will shift towards the side to reduce the overall pressure. Now I'm saying that if the pressure is higher, if pressure is high, the position of equilibrium POE will shift towards the side to favor the lower pressure, which means lesser number of moles, which means more NH3 form. So because of this, this tells us that P1 must be larger than P2. Hence, the correct answer is option A. For question 14, this tests us on the ionic equilibrium. Now, there's no need to compute the value because you notice that the options given is just the workings. So, for question 14, we are given the K value. Now, because we are asked about the pH of NH3, and NH3 is a base, so let me just write the base dissociation equation. NH3 plus water, okay, equals liquid to produce NH4 plus aqueous plus OH minus aqueous. So what we have is a Kb. So what's Kb? Kb is actually NH4 plus multiplied by OH minus over NH3. But because the concentration of this equals to this, so using mathematical technique, essentially this is just concentration of OH minus over the concentration of NH3. But unfortunately, we are given the Ka value instead of Kb. But if you realize that Ka times Kb is equals to Kw, and it's at 25 degrees Celsius, where Kw is 10 to the power of minus 14, that means Kb will just be 10 to the power of minus 14 over 5.6 times 10 to the power of minus 10. That is your Kb value, which is equals to is equals to OH minus square over the concentration of NH3 is told to us as 0.2. Okay, to find the pH, we need to find our POH first. So make OH your subject. So what I have is OH is your OH minus is your subject. So in other words, what we have is 10 to the power of minus 14 multiplied by 0.2, okay, over 5.6 times 10 to the power of minus 10, but we need to do a square root because just now this was OH concentration of hydroxide square. So this is what we have. But we need to find the POH. So a POH is just negative log OH minus. So what we have is just negative log the whole thing, which is 10 to the power of minus 14 times 0.2 over 5.6 times 10 to the power of minus 10. However, the question asks us for the pH, and we know that pH plus pOH equals to 14 because it's 25 degrees Celsius. Hence, pH is simply just 14 minus pOH, which means it's just 14 minus this whole thing, minus this gives us plus, because negative gives us positive. So it becomes 14 plus log square root 10 to the power of minus 14 times 0.2 over 5.6 times 10 to the power of minus 10. Okay, hence the answer for this question is option D, because 10 power minus 14 times 0.2 over 5.6 times 10 power minus 10. So answer is option D. Now for question 15, we need to first decide which one produce a buffer, but what is a buffer? Now, of course, by the strictest definition, buffer is an aqueous solution that whose pH remains relatively unchanged when a small amount of acid or base is added. Well, this doesn't help us to understand this question. Actually, to solve this question, we need to know that buffer must consist of a weak acid and its conjugate base, or weak base and its conjugate acid. So the solution that we are interested in is that it must be weak, plus we need to add its accompanying conjugate. So over here, we have HCl and Na3PO4. So that means I'll just use the ionic equation. What we have is actually H plus your PO4 3 minus to give us our HPO4 2 minus. Okay, so this is our acid and this is our conjugate base. This is our conjugate base, this is our acid. It makes sure that they must be present in sufficient quantity. So if you check, you have 0.05 moles per dmq. I'm using capital M because in some university textbook, capital M represents moles per dmq. So you have 0.05 and you have 0.08 moles per dmq of your sodium phosphate, and of course is equivalent to the concentration of phosphate. And what do you form over here? This will be consumed totally, giving us 0.05 moles per dmq of your hydrogen phosphate. And these are present in sufficient quantity, which means we can actually use our Henderson equation. What's the Henderson equation if you recall? It's actually pH equals to pKa plus log salt over acid. In this case, the salt is our 0.08 over the acid, in this case 0.05, our hydrogen phosphate. Right, so if you know Ka value, you can find the pH. So definitely option A is correct. It does generate a buffer solution. Now how about option 2? Option 2, we have a weak acid, ethanoic acid and sodium hydroxide. So always remember, for you to have a buffer, you must have some weak solution inside, be it a weak acid or weak base. So if you just check, because CH3 COOH plus NaOH, it reacts in a 1:1 ratio. Okay, and you are given 0.08 moles per dm3. Okay, here you are given 0.05 moles per dm3. If they react mix in equal volumes, notice that this will be consumed completely. Yes, although you do get the conjugate base, which is CH3CO minus, in this case it will be 0.05. However, there's no accompanying conjugate acid to match with the conjugate base. So for you to have a buffer, you need to have conjugate acid base pair. So therefore, option 2 is out. There's no buffer being generated. You have a hydroxide, a strong base, and a conjugate base. For option 3, what we have is a ethane dioic acid. Sometimes we call it oxalic acid. Basically, it looks like the COOH2. Okay, if you draw its Lewis structure, you have 2 carboxylic acid group. Okay, so it's triangular planar with respect to carbon, band shape with respect to oxygen. But anyway, back to this question, this is a weak acid. Okay, so plus sodium hydroxide, this will react in a 2:1 ratio, or rather in this case you must have COOH2 versus sodium hydroxide. The mole ratio is 1:2. because it can lose H plus from the ethane diuric acid. So therefore, the mole ratio will be 1:2. So let's check over here. So we have 0.08 moles per dmq of the weak acid, and we have 0.05 moles per dmq of the weak acid. So to form a buffer, you must know that a buffer needs to have a conjugate acid base. At the same time, the conjugate acid base pair differs by a single proton. In other words, it's not really correct for me to do it this way, although yes, it does react in this ratio, but it's better for us to represent this equation in another way, which is this one. OH plus the hydroxide to give you, okay, let me just, I'm just afraid there's no space. Let me just redo this again. Okay, so O plus hydroxide to give you, this must be a full arrow because it doesn't matter whether it's weak acid or weak strong acid, doesn't matter. All right, it will be a full arrow, full reactions. So what we have is this. It will be deprotonated to give you H2O. And this itself, these are conjugate acid base pair. These are conjugate acid base pair because conjugate acid base pair must differ only by one proton, one H plus. So this will be the acid. This will be a conjugate base. Okay. Now the thing is, let's check. The concentration that we have here is 0.05. Over here is 0.08. So this will be consumed completely. Ultimately, what are you left with? 0.08 minus 0.05, giving us 0.03 moles per dm cube with the appropriate volume. Over here, this will be 0.05. Now notice that they are present in sufficient quantity. So we do have a buffer solution. So 1 and 3 are correct. Now question 16. Iron can form complexes with variable oxidation state. Which role gives the correct oxidation number of Fe in the iron complex? Now what you have over here is a hexadentate ligand. In fact, this is EDTA. EDTA. But EDTA has a charge of 4 minus. Where did the 4 minus come from? Notice that this is a hexadentate ligand because you have lone pair from the nitrogen, 2 nitrogen. Okay, they donate their lone pair to the energetically accessible low-lying vacant orbitals of iron. The 4 minus came from COO minus, COO minus, COO minus, and COO minus. Right, this 4 minus is the reason why we have EDTA 4 minus. So that means the oxidation state of iron in this case has to be +2 because +2 plus 4 minus give you overall charge of 2 minus. So this is wrong. This has to be +2. Over here, now this itself is what we call carbonyl. Okay, it's carbon monoxide, but I call it carbonyl. If I'm not mistaken, the name should be tetracarbonyl ferrate, F-E-R-R-A-T-E. Okay, so there's one famous example whereby the central atom is actually nickel, tetracarbonyl nickel, and I think initially people thought that it's an ionic compound, but it turns out that it's actually a simple molecule. But regardless, your ligand over here, or carbonyl, carbon monoxide, does not carry any charge. So therefore, the oxidation state for this case is indeed 0. Alright, so A is wrong. But let's look at C. Now C should ring a bell. C itself is actually our violet coloration. If you recall, the thing is we actually have 6 phenoxide ligands, 1, 2, 3, 4, 5, 6 arranged in an octahedral arrangement. So to test for the presence of phenol, we actually add neutral FeCl3 to form a violet coloration. And this is the violet coloration. This is how you draw the structure, the complex ion. So therefore, the oxidation state of iron is indeed +3 because neutral FeCl3. So the oxidation state of iron is +3. Now over here, this is another famous example. What we have is Fe. Okay, let me just write out. We have Fe H2O5 SCN, overall charge is actually 2 plus. SCN is SCN minus, so this has to be plus 3. In fact, this has a coloration of blood red solution, right? So you learn this under transition metal chapter. So therefore B and B, C, D are correct, only option D is wrong, where the oxidation number of iron has to be plus 2. So answer is A. Now let's look at question 17. Adding concentrated HCl to copper 2 sulfate causes the color of the solution to change from blue to green. Now the thing is, here, right, CuSO4, okay, it has a charge of 2 plus, okay, but in fact, sometimes people probably just write this way, Cu2 plus 4Cl minus, okay, to give you CuCl4, 2 minus, okay. Now this is your blue solution. This is your, what do you think is this color? This is actually yellow in color, yellow. Right, you learn this under transition metal chapter. But how come we have green solution? Because this is reversible, this equivalent reaction. Therefore, blue plus yellow gives you green. Okay, so that means this one is yellow, this is blue, so blue plus yellow gives you green. Okay, so let's come back to this question. Which row best explains this observation? The number of d electrons in copper changes. No, because this is still 2 plus. Over here, this complex ion is yellow in color. So this is also 2 plus. So there's no change in oxidation state. If there's no change in oxidation state, that means there is no change in the number of d electrons in copper. So A and B are out. So you can only consider option C and D. However, the energy gap between d orbital must change because from blue to yellow. So that means there's a change in color. If there's a change in color, definitely the energy gap must have differ, based on the concept known as the DD transition, because most of the organic compounds are colored due to DD transition mechanism. Hence, the answer for question 17 is C. For question 18, compound T is a derivative of a drug used to treat inflammatory and autoimmune diseases. Compound T is treated with hydrogen in the presence of nickel catalyst. What is the number of stereoisomers for the product form? Now, stereoisomerism, we can either have cis trans, sometimes known as geometrical isomerism, or your optical isomerism. But the problem is that when you introduce hydrogen, it's going to reduce your carbonyl group. You have 2 carbonyl groups and the alkene group. Without any alkene, there will not be any geometrical isomerism. But even so, if let's say we do have a cycloalkene, it will also not exhibit cis trans, because cycloalkene doesn't exhibit cis trans. It's only your normal aliphatic alkene that will exhibit cis trans. Cycloalkene doesn't exhibit cis trans because of the steric factor, unless the number of carbon it has is 7 or more. Otherwise, if it's just 6 and below, cycloalkene does not exhibit cis trans. So therefore, your hydrogen is going to reduce your carbonyl and your alkene, but it will have no effect. It will have no effect on the carboxylic acid group. Only your lithium aluminum hydride will reduce the carboxylic acid. So in that case, we should just focus on the optical isomerism. That means we should look for the number of chiral carbon. Right? There's this formula to find the number of stereoisomers, which is question 18. To the power of n plus m. Okay, it doesn't matter which one refers to which one. Okay, one of them refers to the number of alkene that can exhibit cis trans. The other one represents the number of chiral carbon that can exhibit optical isomerism. So therefore, where will you have your chiral carbon? There's one over here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Hence, to the power of 9 stereoisomers for this question. Answer is option D. Let's look at question 19. Question 19. U and V are structural isomers with the molecular formula C7H16. Both U and V produce the same number of possible structural isomers upon reaction with chlorine to form monochlorinated compounds with the formula C7H15 and Cl. So, yeah, which pairs are possible structures of U and V? Well, let's consider option 1 first. So we need to have a monochlorinated compound. So therefore, you can actually form at this position. You need to take note that this, and this are equivalent. Okay, so the other one is over here, 2 and 2, last one is 3. That means this one can actually form 3 possible monochlorinated compound. Over here, we have 1. Okay, either one, these 3 things, these 3 methyl groups are equivalent. So 1, 2. Okay, what else we have? Sorry, there's no 2, there's no H here. 1, okay, so 2. Right, these 2 are equivalent, plus 1 more, 3. Okay, so therefore, option 1 is correct. Okay, so you have to be very careful because the carbon can only form 4 bonds. Now, so how about for option 2? 1, 2, 3, 4, 5, 6. Right? Let me check. Yeah, the other one is just like that. Okay, so the chlorination can occur at this spot. These 2 sides are equivalent. This spot, and this spot. That means this can form 4 possible monochlorinated compounds. Over here, 1 and 1, 2, 3, 4, 5, 6. So this can form 6 possible monochlorinated compounds. So option 2 is out. So let's look at the next one, option 3. Okay, option 3. Okay, now I need to see that actually this whole thing, this ethyl group are equivalent. So 1, 1, 1, 2, 2, 2, plus 3. So therefore, it can form 3 possible monochlorinated compounds. How about here? These 2 sides are equivalent. So 1, 1, 2, 2. There's no H here because this carbon has 4 bonds already. But these 2 sides are equivalent. So 3 and 3. So this can form 3 possible monochlorinated compounds as well. Hence, your answer is 1 and 3, option B. For question 20, equal amounts of compound X, Y, and Z are added separately to 3 test tubes containing equal concentration of ethanoate silver nitrate solution. The test tubes are then placed in a heated water bath. No precipitate forms in one of the tubes. In the other 2 tubes, precipitate form at different rates. Which row in the table is correct? Now, you need to know that actually for this X will not form your PBT. Why? Because the CF bond is very strong. So it's not able to undergo hydrolysis or nucleophilic up. So X, so X itself will not form any PBT. The PBT they are looking for is actually a silver halide. That means it's like AgF, AgCl, AgBr, etc. AgX. So over here, you can only consider option C and D. Now, then the color of PBT which forms the fastest. Now, this is an alkyl halide. This is a acyl bromide, an acyl halide. The CBr bond, yes, CBr bond is actually stronger than a CI bond. However, this is an alkyl halide, whereas this is acyl halide. Therefore, this Br minus will be lost much quicker to form your AgBr, which is our pale green PBT. The yellow PBT is our AgI. However, if let's say this is not acyl bromide, but rather this is an alkyl bromide versus an alkyl iodide, and then the alkyl iodide, the I minus will be kicked out much more easily because CI bond is weaker than the CBr bond. But not in this case, because this is an acyl halide. So the answer for question 20 is option D. For question 21, 3-phenylpropanol and 2-hydroxybenzaldehyde are used in essential oils. Now, just a sidetrack. Now, if the question ever you do not have to know how to name the structures. More importantly, if they give you the name, you must be able to draw the structure. So I actually expect all my students to know how to draw the structures given the name. Okay, now back to the question. which reagents could be used to distinguish between the two compounds. Now, Fehling's reagent is used to test for aliphatic aldehyde. Aliphatic aldehyde. So over here we do have an aliphatic aldehyde. Over here we have an aromatic aldehyde. So we can actually use it to distinguish. So Fehling's reagent will give you a positive test with aliphatic aldehyde, which is this case. So this 3-phenyl propanol will give you a brick red PBT. Okay, this will give you a brick red PBT. Now, some people may think that this is an aromatic aldehyde. No, it's not, because this carbon of this carbonyl group is not directly attached to a benzene ring, unlike this one. So this is aromatic aldehyde, but this is an aliphatic aldehyde. So don't get confused. So one is correct. This one is diamine silver, which is also known as our Tollens reagent. So Tollens reagent is used to test for aldehydes, be it aromatic or aliphatic, meaning that actually both these two compounds will be able to give you the silver mirror, which is your Ag. So Tollens reagent cannot be used to distinguish between the two compounds. SOCl2, you can perform nucleophilic sub against your OH, alright? So yes, we have OH here. Unfortunately, this OH is a phenol, which means that because your lone pair on oxygen can get delocalized into the aromatic ring, hence your CO bond actually has a partial double bond character, which makes it less susceptible to nucleophilic substitution from your SOCl2 to form your chlorobenzene. So therefore, this is not possible. You cannot use it. SOCl2 there's no OH over here for 3-phenyl propanol. So there's no reaction. Although there's an OH, but this one, CO bond has a partial double bond character. So no reaction as well. Hence, the only answer is option A. For question 22, consider the following 4 compounds. What is the relative order in decreasing basicity of these compounds? Now, basicity, we look at the availability of lone pairs. Okay, so now let me just write this out. In order of decreasing basicity, sometimes this kind of phrasing can be a little bit confusing. In order of decreasing basicity, that means you must have the most basic on the left side to your less basic, the least basic on your right side. So that means basicity depends on the availability of your lone pair, whereas acidity depends on the stability of the conjugate base. So if you check this out, now your F itself, a lone pair, okay, the reason why it carries a negative charge because actually it gains 1 extra electrons, but nevertheless the lone pair can get delocalized. So into an aromatic ring, the lone pair can get delocalized into the adjacent C double bond moiety. Same goes for this H as well. So because the lone pair is able to get delocalized, it makes it less readily available for donation, which means that F, G, and H must be weaker base than E. E is a stronger base because this is alkoxide. You have methyl group and alkyl group, which is electron donating, which will increase the electron density on the oxygen, intensifying this negative charge. Hence, E must be the most basic. So look for the option with E on the left side, which is only A and C. Now, next one which we need to consider is this. Well, you'll notice that there's delocalization of electrons for this phenol side, for this as well, and for this as well. However, the delocalization effect is actually much stronger for G and H relative to C, because when delocalized into aromatic ring, it's the carbon that carries a negative charge, if you know the electron drawing. So let me just draw you a little bit of mechanism. Okay, I'm going to use a calculus structure to explain this. So your lone pair is going to, there's a lone pair is going to get delocalized into an aromatic ring. Okay, notice that my arrow it looks something like this. Okay, this is not a reversible arrow, it just tells you that there's resonance structures. So you have an O here, but now this carries a negative charge. Okay, so that means that if you continue doing this again, you see that the negative charge is actually dispersed from this side to this side to this side. That's why it's your OH itself is actually 2,4 directing. But back to this, that means it's your carbon carrying negative charge versus your oxygen carrying a negative charge. Let me just draw this out to show you how it works. O minus is the oxygen that carries negative charge. Oops, I should be drawing this way. Now the oxygen, right, being very highly electronegative than your carbon, is able to bear the negative charge more effectively because of its electron withdrawing effect. So therefore, this is a stronger base relative to your G and H. Hence, the next one will be F. So E and F. Okay, so you can't find a winner between A and C. Now the next one. Yes, there's delocalization into the into adjacent moiety. Right, you have highly electronegative oxygen atom. However, now the key difference is that there's a phenol group, and there's a what do you call that? And a carbonyl group, the ketone. Now this thing here, this OH itself is electron donating. This itself is actually electron withdrawing. So in order for if there's an electron withdrawing effect, so it's going to pull electron density towards itself, meaning that this lone pair is even less readily available for donation, which means that G must be the least basic. This one, because it's electron donating, so therefore it actually increases a little bit of its electron density on the oxygen atom. Because of this, the answer shall be just A. Let's look at question 23. Which pair of reactions could have the same reaction intermediate? For question 23, now, I always ask my student to start off with counting the number of carbon atoms. So you have 1, 2, 3, 4, 1, 2, 3. Notice that the number of carbons has decreased by 1, which suggests that possibly there could be a triiodomethane test because CHI3 is generated, right? One is a step down reaction, or it could be a oxidative cleavage reaction, whereby you cleave the CC double bond. So now for question 1, okay, let me just draw for you the intermediate. Actually, what you have is simply just this one. You actually have a dehydration. Okay, you have a dehydration of alcohol using excess concentrated H2SO4 to form your alkene. After that, what you do is you perform an oxidative cleavage. This is how you get your carboxylic acid. So over here, this is intermediate for reaction 1. Now, then for reaction 2, it will be Br. Then what we have is you have a COH. Now, to get a COH, that means actually what we have is a hydrolysis of a nitrile. You have a nitrile here. So what we have is your KCN in ethanol heat. KCN in ethanol heat to give you a nitrile, followed by acid hydrolysis using dilute H2SO4 heating to give you a carboxylic acid. Okay, so therefore, now some students will mistake this using HCN with NaCN. That one is the reagents used for nucleophilic add. Here we are doing nucleophilic sub, like SN1 or SN2. So we must use KCN or NaCN in ethanol heat. So this is our intermediate. Now for reaction 3, we have a carbonyl. Now this is something that you have to pay attention to. Whenever you have a carboxylic acid and OH on the same carbon, this should signal to you that the intermediate itself is what we call a cyanohydrine. A cyanohydrine. Cyano means you have CN, hydrine means you have OH. And on top of that, because it's carbonyl and the main reaction associated with carbonyl is nucleophilic add, so therefore, what we have is something like this. You have a CN, then what we have is an OH. There's a nucleophilic add whereby you use KCN, then HCN, trace amount of KCN and HCN, a cold condition 10 to 20 degrees Celsius. After that, you perform an acid hydrolysis of the nitrile, which will give you this. So this is the intermediate for reaction 3. Now for reaction 4, you have a diol, and more importantly, this diol itself is on 2 consecutive carbon, which means that prior to that, what you have must be an alkene. It must be an alkene. So you just add co-acidified KMnO4 to give you a diol. So notice that, okay, give me a moment. I think I probably drew something a bit wrong. Let me just check. 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. Yeah, so 1, 2, 3. Okay. Yeah, okay, it's correct. Yeah, this is correct. Yeah, so it's 1, 2, 3. Yeah, okay. So notice that this itself is the same as this. So therefore, answer is just 1 and 4, which is option B. Let's look at the next one, which is question 24. For question 24, which role gives the synthetic route that will lead to the highest yield of the product? Now, for this case, you need to know the order of arrangement. So let's go through all the options. So now, for question 24, let's consider option A first. Okay, so now, okay, we have a methyl benzene. So if you add FeBr3 and Br2, we're going to have halogenation. But because the methyl group is donating, so the next incoming substituent will add at the 2nd or the 4th position relative to your methyl group. Right? So we're just going to follow the question because there's a Br here. So I'm going to add my Br here instead of adding at the 2nd spot. Right? We need to like synchronize the thing. So I just got to put a Br here. So this is what happens after you have added your FeBr3, Br2 to your methyl benzene. Next, we do a KMnO4. This will be oxidizing your side chain, your methyl group, to give you a benzoic acid over here. After step 2 was done for option A. Next, we add concentrated sulfuric acid and concentrated HNO3. This is a nitration reaction. Now, in this case, you always listen to the one that's more electron donating. So compare carboxylic acid versus the halogen. Which is more electron donating? This one. This one. So therefore, the incoming nitrogen ion NO2 plus will add at the 2nd position or the 4th position relative to Br. However, the 4th position has been occupied by COH, so it's going to add at the 2nd position, either here or here. Hence, this is our product. Is it the same as the one that you want to see? No. So therefore, option A is wrong. Let's look at option B. We start off with a methyl benzene. We perform a KMnO4, H2SO4, right? So we are over here. Okay. So, okay, you oxidize it. Then you add your FeBr3 and Br2. This is electron withdrawing group. That means the incoming Br plus, incoming substituent will be added at the 3rd position relative to this COH. That means you're going to have the Br either here or here. Now, if it's added at this position, then there's no need to continue with the nitration step already, because we want the Br to be opposite that of COH. So option B itself is also wrong. Now let's look at option C. The option C itself. Right, so okay. So first we perform nitration. So the nitration will occur at either the 2nd or the 4th position because CH3 itself is an electron donating group. I'm going to add a 2nd position because I want to match that of the product because the NO2 is at this position. So this is what we have, followed by KMnO4, so COOH, oxidized side chain. Now, if you add your FeBr3 and Br2, you won't have any reaction at all already because you have 2 highly electron withdrawing group. That means your benzene is not very electron rich. So it's not possible for the Br to attach to it. You need to have at least 1 electron donating group, or not a single electron withdrawing group. So you have 2 highly electron withdrawing group. This benzene rich is too electron poor to have any further electrophilic substitution reaction. So C is out already. Now let's look at D. Okay, so first you perform nitration. So I have NO2 here. Then I add my FeBr3, Br2. Now, because it's CH3, this electron donating, this electron withdrawing, you always listen to the electron withdrawing group or the one that is more electron withdrawing, assuming you have two electron withdrawing groups. So this electron withdrawing, so therefore you will listen to CH3. So if you add your Br, I'm going to add this position because I want to match that of the product. So I have a Br over here. Lastly, you perform oxidation of the methyl group, you get this. Is this the product we get that we want? Yes, it is. So option D is your correct answer. Next one for question 25. Which product will not be formed in the following reaction? Okay, so we have an alkene here. We have an IBr aqueous. Aqueous means that actually there's some water nucleophile. Now, this is actually a special type of Markovnikov addition. It's actually, we can actually call it a modified Markovnikov. What we learned in the Markovnikov reaction is that H must add to the side with more H. So as you can see here, over here actually there's two H's. Over here there's only one H. We are not going to consider the H over here. We will consider H that's directly linked to the CC double bond. So there's two H, there's one H. So that means you check I and Br, which is more electronegative. Br is more electronegative. This is more electropositive. So you treat this as a H. You will add to the side with more H. In other words, what we have is this. This is what we're going to have with a plus at this position. Okay. So this is what we have. Okay. So okay, I'm just going to match it. Like this is what we have. This is your plus. Okay. Now, so the thing is, you must add the I first, the I plus. Why is that the case? Well, think about it this way. Now, every mechanism tells a story. Every mechanism tells a story. With the approach of alkene, you polarize the electron cloud of IBr so that it will cause a heterolytic fission of your IBr bond. Now, does it make sense that just because an alkene approach and then it's going to cause a heterolytic fission, a breaking of the IBr bond? Well, not really. So for it to break, that means this bond itself must be the weakest. So if you compare the IBr versus, let's say, OH bond in H2O, obviously IBr is weaker. So of course you must target the weakest bond first. Hence, you always break the IBr, at least in this example. Okay, so this is the carbon cation that will be regenerated. So how do we get the option A? Option A will be a major product. Why? Because you have a lot of water. The water nucleophile attack this electron deficient carbon, which bears a positive charge. So A will be the major product. We also have B as well. B will be the next product, a minor product, or maybe the next major product, because your Br minus will attack this positive side. Now, is it possible to get C as well? Yes. However, the thing is, as mentioned earlier, this is a more stable carbocation because this is secondary carbocation because this carbon is linked to two different carbons. If you want to form this instead, it's okay. However, bear in mind that this is a primary carbocation, so it's not as stable, but still it can occur. Okay, so but nevertheless, you must attach the I. But notice for option D, you are not attaching any I. So therefore, this product will never be formed in the following reaction. Let's look at question 26. Now, 26 is a little bit tricky. Now, before I go through this, I'm just going to share this information with you. Actually, I put this in my book. Now, let's imagine that over here, okay? Over here, okay. Now, you do agree that this is a primary Rx, right? Because this carbon is linked to just one carbon. So this is a primary Rx. And the thing is, what we learned is that if it's a primary Rx, we should follow SN2 mechanism. Now, however, I want to let you know that this actually follows SN1 mechanism. Why is that the case? Because it actually forms a very stable carbocation. It can actually form a very stable carbocation. Because your positive charge, let me just draw the calculus structure, can get actually delocalized around the entire ring. Okay, so what we have is something like this. You get a positive charge, then after that, this positive charge is going to get delocalized over the entire ring, meaning this positive charge is effectively dispersed. Hence, it will follow the SN1 route. However, in this question, notice that they didn't choose to put a primary RX. Instead, they put a secondary RX because I think they are worried that students will get confused, and choose maybe option B, the SN2 route. But now that you know that this follows SN1 route, because the positive charge can be delocalized, leading to an effective dispersal of the charge. So you follow SN1 route, that means you should not consider option B because this follows SN2 route. Similarly, you should not choose this as well because if you recall, this is analogous to an electrophilic sub. But we are looking at nucleophilic sub because you have excess concentration NH3. This should be a nucleophilic sub to replace the Br with a NH2. So A is electrophilic sub, not nucleophilic sub. This one follows SN2, B1 and SN1. This one gets a radical. You don't get radical unless it's a FRS, free radical sub. So D is also out, leaving us with this option, option C. SN1 route, by the way. For question 27, now question 27 looks a bit difficult. However, I would say this is probably the most difficult of this whole entire paper. But to solve this question, actually is quite simple in the sense that if you know your degree of unsaturation, the DU, you'll be able to work this out. I put this calculation in my book, so you can refer to that. So in this case, the DU of C4H5O2N is simply just 4 minus 4 over 2 plus 1, okay? Which gives us the DU as 4 minus 2 plus 1, which is 3. So this has a DU of 3, degree of unsaturation as 3. Now, so let's just check. Amide itself has a DU of 1, therefore the DU is 2. Degree of unsaturation is 2, not 3. So option 1 is out. Ester group has a DU of 1, amine group has a DU of 0, so this is DU of 1, not 3. This option 2 is also out. However, ester has a DU of 1, nitrile has a DU of 2. 1 plus 2 gives you 3. Hence, the answer is just B. Notice that if you know how to calculate the degree of unsaturation, this question can be solved really quickly in less than 10 seconds. However, let's assume you didn't learn that. So how can we just work based on information given? Well, the thing is, they say the compound is neutral. If the compound is neutral, the first thing that you should be thinking of is either an ester or an amide. So we have amide here, we have ester here, all these things. We can actually rule out option 2 because 2 is amine. Amine should be basic and not neutral. So option 2 is out. So you just check which options has the option 2. So C and D are out. So leaving us with just 1 and 3. Now next one is that it does not decolorize Br2 in CCl4. So let's check. Does amide decolorize Br2? No, because that one is more for benzene ring and alkene. Ketones as well, does not decolorize. Well, I feel that this part actually is a bit hard to decide between 1 and 3. Right? Because I think information given seems to be so-called incomplete. Yeah. However, if you know, and another way you can see is that, okay, we have O2, oxygen, 2 oxygen. Amide has 1 oxygen. Ketone has 1 oxygen. Ester has 2 oxygen. So it's still 2 as well. So I think for this case, you have to make use of the knowledge of degree of unsaturation. Other than that, I think any other methods is going to be more difficult. So the answer for this 27 is option B. Now for question 28, it's a little bit tedious. It's under ionic equilibrium chapter, soluble product. Okay, so let's see. The soluble product, KSP, of zinc carbonate and silver carbonate in water are shown in the table below. A solution contains 0.2 moles of DNK of zinc nitrate and 0.02 moles of DNK of silver nitrate at 25 degrees Celsius. And these ions can be separated by adding solid sodium carbonate slowly. Which statement is correct? Now, if you say that silver carbonate is precipitated out before zinc carbonate, that means you're saying that it has a lower solubility. Of course, we can just look at KSP to compare solubility. However, we can only compare using KSP if the number of ions present per compound is the same. For zinc carbonate, you have 2 ions. For silver carbonate, you have 3 ions. So because the number of ions present in the carbonate is not the same, we cannot just use the Ksp to compare the solubility. In other words, we actually have to calculate the solubility. How do we do that? Well, we can say that let the solubility of zinc carbonate be X, okay, moles per dm cube. Okay, the unit of solubility is the same as that of concentration. So therefore, let me just write this out. So zinc carbonate to give you zinc 2 plus carbonate ion. So the Ksp will just be zinc 2 plus and carbonate. Let the solubility of zinc carbonate be X moles per dm cube. This one for water. Okay, so therefore this will be X. Hence, Ksp is equals to X squared, and the Ksp of zinc carbonate is 1.46 times 10 to the power of minus 10 equals to X. So X squared. So let's find out what X is. We just have to do a square root of 1.46 times 10 to the power of minus 10, giving us 1, 2, 3, 4, 5. So it's 1.21 times 10 to the power of minus 5 moles per dm cube. This is for zinc carbonate. We'll do the same thing for our silver carbonate. So let's draw out the equation first. Silver carbonate give 2 Ag plus carbonate ion. So the Ksp for silver carbonate expression will be Ag plus concentration raised to the power of 2 multiplied by the concentration of this. Let the solubility of silver carbonate be Y moles per dm cube. So we have 2Y here, you have Y here. So this will be 2Y squared Y, which is equivalent to 4Y cubed. That means 4Y cubed is equals to 8.46 times 10 to the power of minus 12. So find out what Y is. So 8.46 times 10 to the power of minus 12 divided by 4 cube root. So what we have is Y is equals to 1.28 times 10 to the power of minus 1, 2, 3, 4 moles per dm cube. So compare this with this. So which one has a greater solubility? This one has a greater solubility. This is your silver carbonate. Now, if it has a greater solubility, it means that it doesn't form PBT that easily. Now, how do you understand that? Well, just think about it. Moles per dm cube. That means per dm cube of water, you can actually add more moles of that substance. That means it can dissolve better. So that means silver carbonate actually is so-called more soluble than your zinc carbonate. If it's more soluble, that means it will not be able to precipitate out before zinc carbonate, which means that option A is out. Now for B, I've just calculated the solubility of silver carbonate, which is 1.28 times 10 to the power minus 4. It's not 2.28. So that's 2.04, sorry. So B is also out. For C, at any point in time, only one compound, silver carbonate or zinc carbonate, can be precipitated. Yes, any point in time, you can only have one compound, but the key thing is that it's not all. You must precipitate the zinc carbonate first. Okay, there's no two rules about that. It's only once your zinc carbonate is gone, then your silver carbonate gets precipitated out. So C is out. For D, so the only answer is just D. But let's try to work out why the concentration of carbonate ion is 2.12 times 10 to the power of minus 8. Well, they mentioned that when the more soluble compound first start to precipitate, which is the more soluble one? That means it's your silver carbonate. So similarly, let's come back to this Ksp thing. So silver carbonate, right? AgCO3 gives you 2Ag plus your carbonate ion. Okay, so let this be Y. Okay, this will be 2Y, this will be Y. But the thing is, now, the thing is we are actually adding what? We are, the concentration that was given at the very beginning was 0.02. Which means this will be 2Y plus 0.02. Okay, because you have silver nitrate, you see. The silver nitrate will introduce its own ions because silver nitrate, okay, is completely soluble because all nitrates are soluble, so give you Ag plus NO3 minus. So this will be 0.02. This will be 0.02. So the silver ion that we have is also 0.02. Okay, so and then this will be Y. So if you rewrite your KSP, it's going to be look something like this. Now the thing is, the Y itself is going to be lesser, a lot lesser than your 0.02 because of the common ion effect. Alright, so the solubility will definitely be reduced due to a common ion effect. So technically speaking, that means what we have is Ag plus square carbonate ion, but the concentration of Ag plus we can actually simply put it as 0.02 square carbonate we need to find. Okay, and the KSP of zinc carbonate is silver carbonate I mean is 8.46 times 10 to the power of minus 12. Okay, so it's what we have. So solve for the concentration of carbonate. So let's see. Divide 0.02. So indeed, this is the answer that we get, which is 2.115 times 10 to the power of minus 8. This is the value that we get. Okay, so this is how we solve this question. Now actually MCQ is a very good opportunity for us to learn our work. Okay, so I always advise my students that you work through all the options. Yes, although you rule out A, B, C, you think the only answer can only be D, but let's try to spend a little bit more time to understand why in this case the value is 2.12 times 10 to a power of minus 8, right? So they will learn more effectively this way. Now let's look at question 29. Question 29 has to do with anodizing of aluminium. Now to do this question, now let's talk a little bit about the theory. 29, right? So anodizing of aluminium. So we need a power source, right? A DC. So this itself will be your cathode, where reduction occurs, and they usually use graphite as a material to make the cathode. Then this will be aluminium, the one to be, anodized. Over here, the electrolyte I like to use is H2SO4 aqueous. Okay, so now, the key thing to note is that we need to know what are the reaction, the equations, the half reactions, etc. They are involved in the anode side. So let's have a look. Now the thing is, the idea of anodizing is actually to thicken the oxide layer. The idea of anodizing is to thicken the oxide layer. So, So the anode, what we have is that the H2O will be discharged at the anode to generate the oxygen gas. Okay. And then after that, what we have is that the aluminium, it should be 2 aluminium plus 3 O2 to give you 2 Al2O3. The aluminium itself will then react with the oxygen that was produced from the water, right, to form your aluminium oxide, the impervious and impermeable layer. Now we can start to solve this question. Firstly, okay, let's see. The anodizing of aluminium allows highly reactive aluminium to be safely used as a construction material. A piece of aluminium object was placed in dilute sulfuric acid and anodized with a direct current of 1.4 ampere. After t seconds, the mass of the oxide layer formed is 23.7 grams, which expression gives the time taken for this anodization. Now we do agree that the oxide layer is aluminium oxide. So now we know the mass. So let's try to find out the number of moles of aluminium oxide, which is 23.7 over the MR of aluminium oxide, which turns out to be 102. Okay, that is the number of moles of aluminium oxide. However, if you look at the mole ratio, you'll notice that the mole ratio of aluminium oxide to oxygen is actually 2:3. So from here, we actually can get the number of moles of oxygen, which is just 23.7 over 102. divide by 2 times 3. Divide by 2 times 3. But next, let's check. Oxygen to electrons is 1:4. So from here, we can also get the number of electrons being transferred as you need to multiply by 4, which is just 23.7 over 102 times 3 over 2. This is the number of moles of oxygen, but you need to multiply by 4 to get the number of moles of the electrons being transferred. This is what we have. So this is a very critical expression. Next is Q equals to IT. Okay, what's our I? 1.4 ampere. T we do know, we need to find, we leave as T. Now, to find the number of electrons transferred, you need to use Q over the Faraday's constant, which is 96500. 96500. Now we can link these two expressions together, which is just 23.7 over 102 times 3 over 2 times 4 over 1 is equals to 1.4 T over 96500. Okay, so make T your subject. So bring everything up. Okay, all you need to do is just keep all this the same. Okay, notice that we just keep 23.7 times 3 times 4, but you bring your 9650 up. 9650 up. Keep this the same. 102 times 2 times 1. Bring your 1.4 down. So this is our expression. So let's check. We need to have, for option D, right, we have 23.7 times 3 times 4 times 96500 over the 102 over the 1, over the 2 and over the 1.4. So the correct answer for question 29 is option D. Now let's look at the last question. In an electrolysis setup in a beaker, an alloy containing XYZ was used as an electrode as shown. After some time, the amounts of X and Y in the alloy decreased, while unreacted Z was found at the bottom of the beaker. X was also deposited on the platinum electrode. Based on the information above, which options are correct? Now, this question reminds me of the electroplating of copper. All right, let me just recap a little bit. Now, so for question 30, right, if you recall the concept on electroplating, right, they are using inert electrode such as carbon, graphite, but here using platinum, it doesn't make a difference. Over here, what we have is you can actually have impure. Oops, sorry, I made a mistake. This part should be like pure copper. Pure copper. So over here is like impure copper. You have zinc, you have what? Silver. Now, because I noticed that the question told us that the unreacted Z was found at the bottom of the beaker, so it suggests to me that there is a anode sludge. And because of this, I actually link this question to my understanding of the electroplating process. So if you try to link that up, actually this question becomes a lot easier to understand already. Because now let's assume that this is an electroplating process. In other words, the Z itself will just be silver. Z will just be silver. And then they say what? X was deposited. That means X is like your copper. That means Y will just be your zinc. Okay. Now in that case, then we just look at option 1. 2 plus, right? Cu2 plus H2O, H2. Well, this is true because this is plus 0.34 for copper versus the other value I think is, let me just check my data booklet. H2O and H2. H2O and H2 is minus 0.83. Right, so option 1 is correct. Now, another way to see this is that the reduction potential, the one with the more positive reduction potential, will be the main reaction at the cathode. All right, since the question told us that the X was deposited, and we know that since the solution has sulfate and aqueous, well, we do have H2O to give it H2. However, the X is produced and not the hydrogen gas. Therefore, statement 1 must be correct because the cathode reaction, you must have the one that has a more positive reduction potential value. So 1 is correct. Now let's look at option 2. Well, Z plus less than this. Okay. Now if you take Z to be silver, this has a reduction potential of 0.80 volts. Copper is 0.34 volts. This is minus 0.76 volts. So in other words, that means option 2 is wrong already. That means you must change the sign. It should be Z is greater than X greater than Y. Okay, so option 2 is wrong. Option 3, when the polarity of the battery is reversed, hydrogen is produced at the platinum electrode. That's not true, because over here at this point in time, your platinum is the cathode, because it's linked to a negative end, and there's electron flowing to this side, so there's reduction occurring. So this is a cathode. Right, so hydrogen will be produced. However, if you were to reverse the polarity of battery, that means this will be the anode already. Yes, we still have water getting discharged, but the water will get discharged over here to liberate oxygen gas and not hydrogen gas. So option 3 is also wrong. So with that, I conclude my live analysis of the Raffles Institution Year 6 Prelim paper. I hope you enjoyed it. That's it for now. If you like this video, subscribe and hit the notification button so that you don't miss any of my future chemistry videos and live stream. Talk to you soon. Peace out.